Hello, everyone. Welcome. I want to talk to you today about proofs and programs, as you can see. And I think I want first to say thank you to Zishan and for inviting me, and also to Alex for organizing this. I think this conference is a very interesting and very different conference from the ones that I normally speak at. Mustn't forget the clicker. And before kind of talking more about my proofs and programs, I wanted to talk to you a little bit about what the Topos Institute is. Because the Topos Institute is a very new kind of place. It is a startup, but it's a not-for-profit startup. So it's a research institute where we actually shape technology for the public benefit by advancing sciences of connection and integration. And this is kind of cool, right? Because, you know, like most of you here, I've been working in tech, actually in Silicon Valley for 24 years. And there aren't much, I mean, there is academia, and we have lots of lovely talks yesterday, kind of more academic, and some lots of very exciting stuff in industry. But things that stay in the middle between the two are kind of rare. And so yeah, I was saying, I kind of been in Silicon Valley for 24 years, and I started in Park for many years. And then I went to startups and did a failed search engine, but you know, there's plenty of us around. Then I worked in nuance communications, as Zishan was saying, doing NLP and kind of trying to use the voice recognition stuff to do more thinking. And in Samsung, but lately in Samsung, but then I decided that I was going to go back to my roots. And my roots are very different. So my background is, I'm a mathematician. And so I was kind of very worried to come here and talk to you guys, because I thought, well, these guys are not going to understand me very well, because, you know, as you know, mathematics builds upon itself. So, you know, to explain things in mathematics, you actually have to go, doing things over and over and over again so that you get to an interesting bit. So I kind of decided that I was going to talk to you today using stories and philosophical ideas, and I hope you like it. But if you don't and you want to have the real stuff, you can always talk to me in Discord or in Slack or send me email and all this kind of stuff. And I wanted to start on the stories with these three guys on top there. Because, you know, mathematicians have this funny habits of talking about their academic family. So that guy there on the left, with a nice smile, is my supervisor, as we say in England, or advisor, as you say here. And he's called Martin Hyland, and he's considered my academic father. And the second guy there is Robin Gandhi, who was his advisor or supervisor. And I hope you all recognize the guy on the right? Because, you know, I'm lucky enough to be the great-granddaughter of Alan Turing. And that's kind of it's quite special, right? Because, you know, Turing invented computers before there were machines. And I'm going to discuss some of his work here on the proofs that he did and stuff. And later on, he went on to implement the real stuff in Manchester in the 50s. And the guy on the bottom is not part of the family. He is Kurt Gödel. A guy who kind of put some wrenches in the systems that people were trying to do, but that's very much part of my stories to you today. So I wanted to start by saying this business that changing models is really hard. And I mean mental models and mathematical models and physical models. All of them are very hard to change. And I thought I was going to go through 3 kinds of changes of models that with you, kind of starting from the easiest one to the hardest one. And the first one that I'm going to talk to you about is revolution in the sky. Then I want to talk about revolution in mathematics. Then I want to talk to you about revolution in computation, which is the main thing, which I think what you're more interested in. And then, because you're being so nice to sit through all these revolutions, I wanted to talk to you a little bit about the dialectical construction, if you have me. And if Cliff doesn't say that time is up. Why do I want to talk to you about revolution in the sky? Well, first, because you can get very pretty pictures like that one there. And also because when you're thinking about the skies and how people conceptualize space, you are faced with things that are very much on your day-to-day experience. So I don't want you to think about the guy peering outside of the sky dome. I just want you to think about the sun coming up and the sun coming and the moon coming up. Because, this is an experiment that everyone has. And in 1543, Copernicus kind of came in with this theory to try to change this model. So he kind of had been thinking about it since 1514, and you can read lots about it in Wikipedia. But so in 1514, he actually had a trailer, a blog post about his theory of heliocentrism. And, he was going very much against everyone's sensorial experience of seeing the sun come from one side and set down on the other side. And contrary to what you might think, people didn't go against him to begin with. It took 73 years for the church to start saying things against Copernicus' theory. So, and that only started happening because Galileo Galilei came into the story and decided to show people that the earth really wasn't the center of the universe and that mankind wasn't exactly the main creation of God and stuff like that. And in 1615, Galileo started being investigated. Then people noticed, wow, he's based himself on Copernicus, so there's something kind of that we might have to look at. And in 1620, Copernicus' book was corrected. I mean, Copernicus was very worried about this stuff, so he actually apparently only published his book when he was about to die. And legend has it that he actually wake up from a coma, looked at the last page of his book, and died happy. But that's what they say, right? But he was very afraid of what was happening when he kind of moved the earth from the center of the universe like he did. So he kind of wrote a book with lots of if and lots of hypotheses, and instead of talking about things as if they had happened. And Galileo was slightly different, and he started making fun of the people and stuff like that. So the book was corrected in 1620. In 1632, Galileo came with his own book, which was much more on your face. And in the next year, he got under house arrest and died in house arrest. And only in 1835, both of the books were gotten out of the index, the Inquisition index, because between 1543 and 1835, they were prohibited by the authorities. Now, so that was a revolution that took a long time, right? 300 years, or perhaps even a bit more. Now, in mathematics, we also had a revolution, and that's kind of harder to see because people don't really realize what is happening in mathematics by and large. And you know, if you want to read more, and that's just an intermission between the two things that I wanted to talk to you about. So, you know, in 2012, Frank Quinn, important mathematician, wrote this paper called A Revolution in Mathematics, what really happened a century ago and why it matters today. And I recommend you guys kind of going and checking it out. But the main point is that the bulk of mathematics that we got today was crystallized in the last years of the 19th century, first years of the 20th century, and the shock is still being felt. Oops, too fast. And one more. And the thing about that revolution in mathematics is that that it hasn't kind of come through totally yet, right? You know, if you come to a party and you say to someone that you're a mathematician, they look at you and say, oh, that's funny. I didn't think that anyone could do research in mathematics. I thought it all had been done a long time ago. So, you know, people haven't really caught on to the fact that mathematics is a living subject, as living as computing, and everything is happening all the time, and we're building new mathematics every single day. And they also don't realize that mathematics is not about numbers, it's about structures, connections, and especially proofs. And the other thing that, that people don't realize is that I'm kind of using algebra here, not in the sense that you normally have when you're thinking of algebra in 8th grade or anything like that. You know, there's a completely different algebra that has to do with some of the stuff that we heard yesterday. So, you know, people were talking about lattices and groups and monoids and stuff like that. And then, you know, what we have at the moment is that the mathematics that we have, kind of the algebra in this new sense of algebra and the proofs in this new sense of doing new mathematics, this is all kind of happened this century. And you know, the revolution was so complete that it happens everywhere. If you take any undergrad in mathematics nowadays, he thinks that mathematics is about proofs and structures. And if you go anywhere in the world and try to go to the maths department, they don't think that they can do mathematics if they are not doing proofs. So the revolution is completed in some ways and not completed in others. But of course, people here are much more interested in revolution in computation. And the one that I mean is actually the Curry-Howard correspondence. So proofs as types, propositions as types. And this is something that's been going on for quite a while, right? From 1908 to now, and we are still not quite there yet. And I mean, what is the Curry-Howard correspondence? You know, in Papers We Love, 2015, you had a beautiful talk by Phil Wadler exactly about that. And the video is up on YouTube. Everyone can go and watch it. So, you know, why am I here trying to tell a different story about the same subject? Well, the reason I'm here trying to talk to you about that is because, as I say, this stuff is not done. You know, it's very hard to see change while you are in the middle of it, while things are happening still. And the traditional Curry-Howard, which connects intuitionistic propositional logic, simply typed lambda calculus, in Cartesian closed categories, it's been in place for a relatively long time, since the 60s, 68, 69. But that's only one edition of it, one version of it. And what I'm trying to sell to you today is actually the fact that you can have several different Curry-Howard correspondences. The thing that you still need to have is the connections between logics And that's another thing that people don't understand. If you say, I'm a logician, I deal with different logics, they look, what? Isn't logic a single thing? Isn't that either you're logical or illogical and that's it? And it's not. And that, I think you all know that, that we have different logical systems for different applications, different uses. So this is the traditional Curry-Howard. And how this came about, why I'm talking about revolutions in computation and kind of talking about something that happened in the 60s. And here, I'm actually kind of very happy that yesterday we had so many wonderful talks about similar stuff, right? Because everyone should know by now that the Curry-Howard is a fundamental result connecting logics, programming languages, and categories. And that the original Curry-Howard ties logic and type theory. And here's where I depart from Phil Wadler's stuff, because Phil kind of talked very much about type theories, that is programming language when you implement them, and logics, different kinds of logics. But I want you to make sure that you see a third side of the Curry-Howard. I want you to make sure that you see the left side there, where we have Bill representing mathematics, proofs, and in category theory. And I wanted to make sure, that if you want to understand this stuff properly, if you want to make sure that you can see why the fat arrows there really exist, then you have to do the hard work. I'm not going to kind of do the hard work for you right now. I'm just going to try to show you where you need to go and look so that you can see why having these fat arrows is important. So let's see. So each one of the arrows connects two different fields, and you can look again on the YouTube video of Phil Wadler's. Whoops, too much. But why this thing kind of came about when it did? And the reason is because mathematics was in turmoil at the beginning of the last century. In 1906, Bertrand Russell came up with his famous Russell paradox, and people realized that even if you are careful while you're thinking, and even if you were trying to formalize your thoughts and stuff, you still could get into paradoxes. And Hilbert, the guy with this hat, came up and said, well, we need to kind of formalize things, and we need to make sure that we can prove some of the special properties of all of mathematics. He actually wanted to base everything on finitistic methods, and his first most important goal was to prove consistency of arithmetic. So, things like dividing, sharing bills in bars and stuff like that, adding, subtraction, dividing and stuff should work the way we expect it to work. And Hilbert had this wish list, and I had taken off this slide before because I thought you guys wouldn't like to hear about extra properties like consistency and completeness and conservativeness and decidability. But, I think May did a wonderful job yesterday telling us how we need consistency just to kind of run tournaments all over the world, and how you actually need completeness, otherwise you cannot prove that you actually have the correct players for your games. And she didn't use the word conservativity, she used monotonicity, but it's a similar sort of idea. So Hilbert wanted mathematics to satisfy all these four properties, and I'm sure you agree with me that they are sensible properties, that we want our systems to satisfy these things as much as possible, right? Because we also want our systems to do things for us. So Gödel, the guy that I put it in the same slide as the family slide, was the guy who destroyed the idea of Hilbert's program with his incompleteness theorems. And I'm not going to talk to you about incompleteness theorems because there's lots of people who like to talk about that, and I'm not particularly fond of. But Gödel really proved that Hilbert's program is impossible if you interpret it in the most direct way. But of course, logicians did not go to sleep and decided that things could not be proved consistent. They just decided there are ways around that, and there's things that we can do. One of the things that we can do is we can use more powerful methods, and we're going to see that in a minute. But the other thing that you can do is that you can do something called proof theory, and you can actually, where you can actually try to see how much you can prove with whichever methods you can use. And that is what my wartime proofs are about. Because in 1934, Gerhard Gentzen, who was an assistant of Hilbert, came up with the two systems of describing logics that you all used when you use BNFs and inference rules and you use semantics of programming languages and stuff like that. So these systems are called natural deduction and sequent calculus, and they are the main proof systems used nowadays by everyone. And the same guy did both of them in one paper in 1934. And we don't talk much about him because he was a prisoner of war on the other side and died in prison, so it's a bit of a difficult story. But Gödel, back to him, he had a different way of trying to go around the problems of incompleteness. He proved incompleteness. He was the guy who broke up the Hilbert program, but he actually believed in the same things that we were saying a minute ago. He also wanted to prove consistency of arithmetic, and he had his own way of proving consistency of arithmetic. So we say sometimes that he had a liberalized version of Hilbert's program, and he just wanted to justify the systems that we have in terms of notions as intuitively clear as possible. And you know that intuition is the stuff that is being running through my revolutions, right? So he came up with the notion of computable or primitive recursive functions of finite type. And then he used the Dialectica, which we'll see in a minute again, to try to go around the no-go theorem that he himself had created. And I've been talking about wartime proofs for a long time now, 20 slides. And what about the programs? Well, the programs, we had lots of interesting things about them yesterday too in Doug's talk, right? Because the fact is that when people started thinking about computing as a machine-like activity, they came up with different notions of computable or effective computations. So Alonso Church came with the lambda calculus in 1932, and he came up with this idea that a lambda term, each lambda term is a machine computable function, and every machine computable function is a lambda term. And I thought, you guys are going to have to take that on trust from me. But you don't, right? Because, yesterday Doug showed you that you can take the whole of the C programming language and translate it into lambda calculus completely. And you can go and check it in the web if you want. So yeah, I think people do feel that machine computable functions are lambda terms. And Haskell Curry, we also heard about him yesterday because we also heard about combinators and combinatory logic. And that's where I'm getting the 1908 sort of number, because Sean Finkel died very young too, and in 1908 came up with this idea that you could do all this stuff with S and Ks, like again Doug showed yesterday. And then my favorite guy, Turing, came up with his own version and came up with the notion of a Turing machine and explained why this was what a computable function should be. And then we now have Church's thesis that all these things are equivalent. So, it does look like we are actually doing this business of investigating the structure of the universe and finding the structures that are underneath things. Now, I kind of was worried that I had to, that you wouldn't like to see any mathematical symbols. I shouldn't have worried. People yesterday used lots of taus and gammas and sigmas and stuff like that. But, you know, I can also think about traditional logic. And, you know, guys, this is Middle Ages logic, right? This rule on the left, if I have that A implies B, and I have an A, then I prove a B. This is modus ponens. The monks in the Middle Ages were using it. The other side is a little bit more complicated and a bit more like stuff that you guys like to do, right? Because it's this idea that if I assume an A, and I do a collection of operations over this A, the things that I'm kind of putting the 3 dots and calling it a pi, and I then derive a B, any B whatsoever, then that is something like an implication. It gives me an implication, A implies B. And in 2023, I can just do Curry-Howard very easily by adding terms to it, adding lambda terms, M, N, application of M to N, X, a variable of type A, M, deriving an M of type B, and then getting a lambda abstraction. So that is all very easy nowadays. And as I was saying, kind of lambda calculus is, by all accounts, a universal programming language. But yesterday, again, we did see lots of other things that are a little bit more complicated than lambda calculus and pure functional programming, right? We kind of want to do things like distributed computing, we want to do parallel programming, and we want to do all sorts of interesting effects. And these things are active areas of research, but most of them we are actually trying to attack using extensions of the Curry-Howard correspondence. So, you know, even locks and unlocking and unlocking threads and stuff like that, there are ways of doing these things using versions of Curry-Howard. So we do have a cornucopia of new logics and new program constructs based on the correspondence. And that's before you start bringing in the heavy machinery that is category theory. So I want you to think about, I mean, I'm not going to give you definitions of categories, functors, and natural transformations, but I'm going to remind you that that the same way as kind of calling algebra some things that started from solving simple equations in 8th grade, and then I made it algebra, a name for all of this stuff. Well, category theory is a little bit like algebra on steroids. And the hard bit here, when you kind of try to make this correspondence stick, is actually finding, and it's kind of it's a little bit on the small words there, appropriate, right? You have to find an appropriate category, an appropriate morphism in this category, and appropriate logical constructors, and all the thing has to satisfy certain conditions. But we can do it, and you can do it for several logics, like intuitionistic logic, system F, polymorphism, dependent type theory, linear logic, modal logics, classical logics. And I think, you know, you can see that lots of the systems that we have been talking yesterday and today about, things like Rust and Haskell and OCaml, they're all based on these ideas of Curry-Howard correspondence. And more to my point, at the moment we're doing things with theorem provers and proof assistants, so Koch, Isabelle, Lean, all this stuff is based on variants of Curry-Howard correspondence. And I kind of have a few more pictures here just because they are the ones that I worked on personally. So I worked on linear lambda calculus, and kind of you heard yesterday from Amal that it is part of what is happening in Rust. It's affine types, but they are like linear types. I worked in modal correspondences, and we actually use that for all sorts of interesting stuff, like monads and comonads are versions of modal logics, and hence we can use it for all sorts of effects. And even the linguists can use that for syntax, in things like the Lambeck calculus. But, and now I have to see how I'm doing. I'm good, good. Because I wanted to talk a little bit about something much more recent than the stuff that I was describing before, which is kind of beginning of the 2000s. So I wanted to talk a little bit about about that trick of Gödel that I started talking about a minute ago, about trying to prove that the consistency of arithmetic with different sorts of means, and means that are actually things that you guys might like better because they use types and functionals between types. So what did Gödel do? And again, it's another one of these things. He also had a trailer or a blog post in 1942, but he actually published it in 1958, this Dialectica interpretation. And it's called Dialectica not because of anything to do with Hegel or anything like that, but just because it was published in the journal Dialectica. And his idea then was to, Gödel had lots of tricks up his sleeves. He had lots of things that he could do that people couldn't see why or how they worked. So the thing that he did for the Dialectica was to say, oh, okay, guys, you only have to think about constructive functionals, because if you're thinking about the classical ones, I did some interpretation of classical logic into intuitionistic logic that will solve that bit for you. So we only need to prove HA, which is Hyland arithmetic, consistent. And then he said, okay, the other thing that we can do, if we take any formula of Hyland arithmetic whatsoever, so, all sorts of interesting functions there, he said, I can always make it into a normal form that's very strange, because its normal form is of the shape that exists in U for all x, and then something that's related to the A, but it is quantifier-free. So, you're simplifying your life quite a bit by taking things that are quantifier-free, but putting at the beginning, a prenex, one existential and one for all. And then he defined this translation by several clauses recursively on the connectives to unpack a formula. Whatever formula you're given, you just go unpacking it to get to the base case where you know it's true. So it's easy to prove the theorem. Easy. I'm lying here. It's easy if you're Professor Troster or if you are one of those guys. You can prove that the theorem that he wanted, meaning consistency of Hyland arithmetic. But it's very hard to see why it works. And then that's when I get into the picture, because in 1988, long time ago, I actually provided a categorical model of Gödel's dialectic interpretation in my PhD thesis. And okay, I said I did not want to give you many symbols, and that is the only slide that has real mathematical symbols. So bear with me while we go over it. Because what is happening here, it's actually very exciting, and to my mind, of course, and also very interesting, so kind of historically speaking. Because what you kind of want to do is you want to understand where the dialectic interpretation comes from. So you want to kind of transform that into structures and algebraic structures of a kind of higher kind of stuff. And what you can do is, you take the shape, this thing should, you take the shape of the formulas that Gödel plucked out of his unconscious, the existent U for all x, alpha of ux or a of ux, and you transform that into a category which has objects, triples, a type for U, a type for X, and some sort of relation between the U and the X that I'm calling alpha of UX. So far, so good. You know, you're just saying, okay, if he managed to do this translation and make everything becomes of this shape, then we can think about that with this easy categorical structure. But here comes the real important and different business, because, you know, when you kind of want to show that one formula in Hyland arithmetic proves another formula, so you have an A of that shape, there exists a U for OX, alpha of UX, and there you have another one, so a B of the shape for all V, there exists a V for all Y, beta of VY. And then look at that, guys. I mean, do you recognize the kind of functors, the kind of functions that I'm kind of giving you there? I'm giving you a little f that takes U to V, meaning I'm mapping the existentials, one existential to the other existential. And that makes sense, right? Because, you know, if I want to prove an implication, I want to apply the implication to witnesses of the first guy to get a witness of the second guy. But then comes the big jump of Gödel, which is to say, it's not only that I preserve the proofs of the things that I'm showing, I actually preserve the proofs, but I actually map back the counterexamples. I take a counterexample of the B and I send it back to a counterexample of the A. And, you know, you guys rediscover that, right? Because these are lenses. They are just what you think about when you're doing lenses in functional programming. And that's something that Gödel kind of came up with in 1958, that, you know, that lenses, sorts of morphisms, transformations of lenses, are a very good way of preserving truth of formulas and actually kind of a way of crystallizing everything that you need to know about this formal system. Now, the other bit of very exciting news is that instead of just, you know, you'd think then that you start from a model of the simply typed lambda calculus, a category C, and you do this construction and you'd think you'd get another Cartesian closed category, because you'd think that you're doing the things as constructively as possible, but you get a model of linear logic instead of constructive logic. And that is kind of very different. So I am kind of getting up there. So the point of this dialectical categories or these constructions is that, as I was saying, Gödel proposed that in 1940. In 1958, he actually published it. In 1998, there was this first categorical interpretation. In 2008, people started generalizing for different logics, and first for vibrations and kind of polymorphic types, then more modern versions of vibrations. And 2018, Tamara von Glen and Sean Moss showed that you could do that for dependent type theories. And very recently, this year, with Trotter and Spadetto, we've been showing that that Gödel's argument really is kind of universal in some ways. That is not just that you can construct a model satisfying these things, but anything that satisfies the properties that we want of a logical system kind of ends up being one of these Gödel vibrations. So we have lots of applications in CS. So things like concurrence theory, linear functional programming, partial compilers, the lenses that I just kind of described, and even automated differentiation is one of the new things that we're doing. So I want to close up here saying that, yeah, changing models is very hard and it takes a long time. I think that despite all the good work of Phil Wadler, we still have the Curry-Howard being very underappreciated. And I think it's very important for things like strange loop and papers we love, because it's very important to have this kind of interdisciplinary work between math, logic, and programming. And I showed my example, and maybe I shouldn't have used so much time on my example, but I think there are plenty of other applications to develop nowadays, and I thank you very much.